Okay. Hi. We can start.
We can start now.
Now, yeah.
Okay, thank you very much. So we wait for 8 minutes. Do everybody hear me? No?
Yes.
I can hear you.
Okay. That's fine.
Perfect.
Okay, so let's start the first part of our mini symposium for 2023. Today we have, in the first part, we have 5 presentations. Each presentation should take 20 minutes, and I strongly recommend to talk less than 20 minutes and save time for questions and comments. Okay? The first speaker is on site, as I understand. Right?
Yes.
Yes.
Okay. So Daniel Kozidenov speaks. Thank you. Please.
Hello. Do you hear me?
Yes.
Share the screen, right? Excuse me. Share the for share.
One moment. Is in Greek.
This one.
Yeah. Okay.
Do you see
Can you
my
see-
screen?
Yes, we can see.
Okay.
Could you please to do full screen?
So for the technical issues, here they cannot see that.
What is it? Excuse me. It's in Greek.
So we cannot visualize. Yeah.
No. Yes,
This is a common problem with.
yes, but the full screen.
F5. We don't do that because there's a problem with projector. So it will have to be presented
Sorry.
in this way. Όχι, μόνο με το μόνο με το LibreOffice. Αλλά όταν το κάνεις στο LibreOffice αλλάζουν τα πράγματα.
No.
No. One moment. No, one moment.
I want to press escape.
And this.
Because
Okay, now we see full screen, please.
Okay. Just this, this
Yeah.
one. It's not the blue.
This one?
Yeah. No. Okay.
So do you see my screen?
Yes.
Now full screen,
We see
right?
Full screen, please.
Okay.
Start.
Okay, let's start. Let me time. Hello everyone. My name is Daniel Kazdenov, and I'm from Nazarbayev University, which is located in Astana City, Kazakhstan. And today I'm going to talk about the optimal time-step relationship for couplet CFD and DEM simulations in sand production process. This is this is extension of our main work where we investigated the sand production mechanisms, and this work has been done in collaboration with Sagan Omerbekov and Yerlan Amanbek. And so sand production is a major problem in oil and gas industry, and it usually occurs with unconsolidated sandstone reservoirs where the sand formation exceeds the mechanical strength of the reservoir rock, and it has a lot of negative effects. For example, it blocked the flow lines and destroys the equipment by erosion, and that's therefore it limits the productivity and brings a lot of financial issues and causes significant disposal challenges. And to minimize those limitations, we need to optimize the best strategy for sand control management by by predicting the sand production. And the discrete element method coupled with CFD is one of the popular instruments to study the sand production mechanisms at a microscale level. And in the discrete element method, so the discrete element method can describe the motion of the particles and characterize the interaction between the particles. And also it can track the trajectory of the particles. And also it can describe the particle fluid interaction forces because it can be coupled with CFD. It also, so it allows us to perform accurate modeling at a micro level when the real laboratory experiments are difficult or expensive. On the other hand, we face some challenges when we use too many particles. The computational cost of the simulation increases, and also we have to select the optimal time step relationship between CFD and them to perform accurate modeling and to perform accurate and efficient modeling, and also physically relevant. So to solve those challenges, our objectives are the follows. Numerical. So we're gonna numerically investigate the correlation between them and CFD time steps, and also we will reduce the computational cost of the simulation by selecting the optimal time step. So first we will talk about the model formulation. Then we will analyze the obtained results, and we'll finish our presentation with conclusions. So Newton's second law described the translational and rotational of the particles, and the interaction, particle-particle interaction forces can be described by force displacement laws. And the particle fluid interaction forces are the sum of the forces exerted on a single particle by a fluid. And we use a model A version of the locally averaged Navier-Stokes equation, where the fluid occupies only the porous fraction of the material, and the forces such as pressure gradient and viscous forces and gravity and drag forces are shared between solid phase and fluid phase. And for the drag force, we will use de Felice correlation. And so in this slide, I'm going to show how we calculate the critical time step for discrete element method and CFD. For discrete element method, we're gonna use the Rayleigh time step, while for discrete element method, the critical time step is calculated taking into account material properties of the particle and the size of the particle. In the CFD, the Courant-Frederick-Levy condition, so it calculates the critical time step taking into account the size of the CFD cell. So the flow should not travel over the one CFD more than in one time step. So we use consecutive coupling regime between CFD and them. As you can see from the picture, the data information occurs after each other. So as you can see from the picture, the time step is usually much smaller than CFD time step, and we define the coupling number n by the ratio of the DEM time step to the CFD time step. So in this slide, this slide represents the visual representation of the numerical model to the experimental setup, and we could numerically reproduce the experiment by using around 33 particles, and we selected the section over here from the middle of the real laboratory sample. Excuse me? Point. Okay. Yeah. Okay. And so before the CFD and then coupling, we prepared our numerical sample, and we used already calibrated material parameters which were obtained from another work. So details can be found below. And we use particle size distribution from Kazakhstan field. And first of all, we generated our particles, and we use common Hertz modeling, contact model to avoid any cohesion effect between the particles during the particle generation. And then we compressed, and during the compression, then we compressed the sample, and we achieved 1 megapascal overburden pressure as in the laboratory experiment, and also we achieved the porosity of the 42%. And during the perforation, as you can see from the screen, we used modified version of the GKR contact model, where we represent the cementation behavior of the sample. And you can see from the video, during the perforation, the penetrometer break the particles of the numerical sample. So the blue color represents there is no bonding, and red is there is more than 4 bonding. So next. So and then after the preparation of the numerical sample, we started the CFD-DEM coupling. And here you can see the DEM geometry and CFD boundary conditions in the CFD part. So we use unresolved case where in the one CFD cell we can place several small particles, and DEM time step was 10⁻⁸ second, which is within the limitation of the Rayleigh critical time step. So for the CFD part, we used fluid was water, and we used transient incompressible laminar flow. And the solver was CFD-DEM solver, piezo, based on the piezo solver. And we used here 4 cores for the parallel simulation. And the fluid was injected from the sides, the green color, and here from the both sides. And the gray color was periodic boundary conditions, and from the outlet on the top and bottom, we placed the atmospheric pressure. So below you can find the software and HPC configurations. So first of all, we validated our numerical results with the experiment. And so this validation was performed in the previous work. The details are below. And in the validation, we used normalized time period and normalized cumulative sun production rate, since the experiment and numerical simulations were performed in different conditions. So here is the visual representation of the simulation result. And so on the left, you can see the CFD part, like fluid flow computed by CFD. On the right, the movement of the particles computed by discrete element method, and everything happening at the same time. So just a quick remark that at the beginning, due to the high pressure in the system, high difference, like large difference in the system, there is a like intensive movement to the top of the sand particles, and we see the intensive sand production. And on this slide, you can see on the left, you can see the captures of the main event from the previous video. On the right, the cumulative sand production rate of the different coupling numbers, which we selected 4 different coupling numbers, and we compared the cumulative sand production of them. So as you can see at the beginning, during the intensive sand production, we see that the cumulative sand mass was the same for each case here. And then like during the constant sand production and transient, when the sand production becomes transient, the sand production rate was different in each cases, but overall they have the similar pattern throughout the simulation. And in this slide, I'm going to talk about the bonding behavior of the particles during the coupling. So on the left top figure here, you can see the plot of the total bond number versus time, and during the intensive sand production, we see that the total bonds in the system, there is a sharp decrease of the bonds in the system, but after about 0.01 second till the end, we have the stable bond number. It means that there was not bond breakage due to the flow. And from this plot, we can see that the fluid flow also has effect on the bond breakage at the beginning. And during the stable bond number, we see that there is a sand production. It means that sand production occurred by already broken particles in the system. And on the bottom here, the plot shows the bond ratio of the bond ratio and versus time. The bond ratio is the ratio of the bond number in the system to the total contact number in the system. And we see that the sand production also, we can see from here, from 0.01 second, the bond ratio increases, which means that the sand production occurs. And this means that the contacts are losing from each other. And on the right side, we can see visual captures of the bonding effect. So the first top plot represents the initial bonding and after the perforation, and then the middle and the last one shows the bonding behavior at 0.01 and 0.04, and we can see that the fluid during the intensive sand production eroded the side particles from the perforation area, and this causes the total sand production of the system. And we noticed that also. So this there is the similar pattern at 0.01 and 0.04 in terms of bonding behavior. So this also, in addition, we measured the CPU time and calculate the speed up, and also we calculate the relative error of the obtained results. And from the CPU time and speed up and overall sand production, we can see that the faster, in terms of CPU time and speed up, we can see that the coupling numbers 100 and 1000 show the faster acceleration. But in terms of relative error of the final sand production at the final time and bonding behavior, we see that coupling numbers 10 and 100 perform well. So in conclusion, I want to remark that we performed a numerical simulation of the sand production by using the modified GKR contact model for cementation, and we analyzed the fluid flow in the system, and also we examined the bonding behavior of the particles at different sand production regimes. In all cases, we noticed that CPU time is significantly reduced compared to the coupling number 1. Particularly, the fastest acceleration was at coupling number 100 and 1000. And the speedups, they show the similar speedup, about like 8.8 and 9 and 5. The other results like bonding behavior and final sand production results, they show that coupling number 10 and 100, they show the accurate results. So in the future, we are investigating the effect of polymer injection on sand production, and we have obtained some results. And we made a model like taking into account the rheology of the non-Newtonian fluid. So details of those obtained results can be found below. And here is the references which I used. So thank you very much, and I would like to acknowledge the following the project grants. And thank you very much. If you have questions, I am ready to answer.
Well, thank you for your presentation. We have time for one short question. Any question?
Hello, may I ask a question?
Yeah, please.
Do you have any suggestions about what reasons result in the increase of relative error for the largest number of elements? Can you jump to slide 15, please? The table.
Yes. So this slide.
Yes.
Can you please repeat your question?
Do you have any suggestions about what reason results in the result in the fifth column for final sand production for the largest coupling number?
For this one?
Yes.
So why was that large error, right?
Yes. And is there conclusions that we should investigate some coupling numbers between 100 and 1000? Is there any sense?
1000, right?
Yes.
Thank you very much for your question. So I think there is there is a negligible difference between the coupling numbers between the 100 and 1000. But from the final sand production, so the 100 means that we increased our CFD time step, right? We used here, let me show so for 1000, we used 1/10 of the -5. So I think that this time step for CFD coupled with them is large, and for the coupling processes, it shows not physically, so we lose some physics, and that's why we see from these numbers. So if you compare, we have like a large, much larger error here, and also here, and relatively, and also here compared to those errors. So from the results, I can say that we have to select the optimal coupling number and to perform accurate modeling. And I think we lost some physics here, over here.
I see. Thank you for the answer.
Okay, so we have no time for questions anymore. So let's start the next presentation. Next speaker is Vadim Lisitsa. Please. Please share your screen.
Yeah.
Can you see my presentation? Can you hear me?
Yes.
And can you see the presentation?
Yes.
Great. So, good afternoon, everybody, or good evening. Mainly good evening, everybody. So, my talk now is about the simulation of two-phase flow in models with my microporous material. So, the statement of the problem is the following. So pretty much everyone in this world is able to simulate 2 or even 3 or multi-phase flows in porous materials, in porous space of the porous materials, and this is indeed quite a hard nut to crack, but it's done now. But what is getting more and more important nowadays is to be able to simulate fluid flows in porous materials where big pores are filled with the microporous material. I mean, you've got macropores where you can expect the free flow in these pores, and some pores are filled with macroporous materials, well, where we expect like filtration regime of multi-phase flows, and that's what we were working on. And if we consider this particular figure, especially on the left, the red guys are open pores where we expect the free flow, and this colored guy with the color changing from light blue to red is the microporous materials, and these different colors correspond to the different porosity. And the blue guys is the matrix of the porous materials, which is absolutely impermeable. So, and that's what we try to simulate. Okay, once again, the red guys are open pores, the colored guy is the permeable microporous material, and the blue guy is absolutely impermeable matrix. Okay, what we are gonna do here. So as I told before, we expect that the Navier-Stokes equations are governed in open pores, and we expect Darcy flow in the porous material. And we know how to couple them. We need the pressure to be continuous, and the flow to be continuous through the interface between the open pores and the microporous material. However, we are not that happy about solving this these two equations and couple them explicitly, and we go to the Navier-Stokes-Brinkmann equation, which is presented over here, and we where we add the filtration term in Navier-Stokes equation, and then playing with porosity, which is phi over here, we can go to either free flow regime or filtration regime, and that's what we are doing about the flow. Now the flow is okay. The main problem here is what to do with phase transport, and to do so we focused on the following approaches. So in the open space, or in the open pores, we are solving Cahn-Hilliard equation, which is it's a phase field approach where we represent each phase as a well, where the phases are represented as the continuous function phi with a smooth finite interface between the phases. And we also need to satisfy it satisfies the Cahn-Hilliard equation, which is presented over here, and we need to state the special boundary condition, which is the boundary condition for the weighting angle. And in the particular figure, you can see the example of the weighting angle equals to 130 degrees. So it's pretty much impermeable blue liquid on the ground. Okay, so this approach is also well known nowadays, and we're using it. Just another example of the weighting fluid. And then we need to do something with the saturation inside the inside the microporous material, and to do so we are solving by Clay-Leverett equation, which is presented over here, and S here is the saturation. So it's also a well-known approach. If we are talking about just simulation of the fluid flow in porous materials, multi-phase. Two-phase fluid flow in the porous materials, this approach is widely used, and the trickiest thing here is how to combine them. So okay, once again, in the open pores, in the red guys, we can solve Cahn-Hilliard equation with all the boundary conditions to satisfy the weighting angles and stuff like this. In the colored guy, microporous material, we can solve Clay-Leverett equation to simulate the phase transport. What should we do at the interfaces? And if we play a little bit with the equations and represent both of them in like divergence-free form, we can finish up with the continuation of the flows of the fluxes, and then this would look like on like what is presented in the middle of the slide. So, and the trickiest thing here is that we need not only satisfy the continuity of the fluxes, but also we need to impose the boundary condition, weighting angle boundary condition in the open pores. We cannot avoid this condition here, and that's why we still have to solve these equations actually separately. So we solve Cahn-Hilliard equation in the open pores, we solve Clay-Leverett in the macroporous materials, and then we combine them at each interface. That's an unavoidable step here, unfortunately. And that's what it looks like. So that's how it works. And now just a few examples of that this approach works well. So the first example is what we did. We placed a droplet on the impermeable wall. The droplet is the blue guy. It's an unwetting phase, and you see that everything is great. This is pretty nice. the shape of the droplet is what it's supposed to be. The pressure difference inside and outside of the droplet pretty satisfied the theoretical estimations pretty well, and everything is great. So pretty much this the same example, but for the wetting phase. And again, the shape is okay, the pressure difference is okay. So after that, we took the results of these two simulations and then put the and let the wall to be permeable. So now the wall is not just a wall, but it's a permeable material, microporous material, and we decided to take a look on what would happen if this droplet would appear on the permeable material, on the permeable microporous material. And if the droplet was like unweighting, if it was an unweighting phase, then pretty much no fluid penetrates inside the microporous material, because well, it's not supposed to be. Just some fluid goes there just to equilibrate the pressure, but not it's not that strong. The effect is not that strong. Quite small amount of fluid is needed to equilibrate the pressure. If the phase was wetting, it goes inside the porous material quite nicely, because capillary pressure sucks allows the droplet to penetrate inside. And this was one example, and the other example, when we add the external flow, we add the pressure gradient on the right and the left, and then we we simulated the external flow goes from left to right, and that's what is going on in this situation. So we have external force to push the droplet inside the permeable material, and then it goes out the permeable material because it doesn't really like to be there, but it goes along the main flow, and you see that the droplet forms when it goes out from the porous material, and then it flows away from the computational domain. And pretty much the same simulation, but for the wetting phase. And you see that for the wetting phase, we have quite a large amount of fluid staying inside the permeable material, because capillary pressure keeps some fluid inside this microporous material and doesn't let it go out. That's how it works. And the last example is the part of the real life CT scan of geological formation, and with one large microporous, with one large pore filled with porous material, and then several small open pores, as you can see on the left, and then and on the right is the representation of the phase saturation. So we fill the material with the wetting fluid, yeah, and that's how it looks. So that's pretty much it. What I have presented is in mathematical model, which allows us to combine the free flow and the filtration flow in the same simulator. And this simulator was actually this approach. Well, the algorithm was implemented, and we developed an algorithm based on CUDA technology, so we can do this simulation quite fast and do it for different rock models. That's pretty much it. Thank you for your attention.
Okay, you save some time. Thank you very much for interesting talk with nice pictures. Any questions or comments?
In the room, no?
In the room, no. Okay. One short question. Have you studied the convergence of the method for in some problems or not, how it works? Is its accuracy and so on, so on?
So actually, the only thing where we can really investigate something right now is the simplest one, with a droplet on with a droplet put on unpermeable material. Where in this case we know what the shape should be, what the pressure should be inside and outside, and so on. For the permeable material and for the saturation of the permeable material like this, right now I don't know any appropriate test cases, because everything we can do, we can study separately the free flow and the filtration flow, because for both of the problems are well known. Well, for both problems there are analytical solutions or previously done simulations or something like that. But for the coupled problem, there is only one group working on this. They're doing simulation using volume of fluid method, and I haven't seen the results where the droplet goes out of the goes out of the permeable material. This experiment with the droplet going out like here, it's I haven't seen any publications or presentations on that. That's
yeah. This picture is really impressive, so I like it. Okay, thank you. Any other questions? No. So now we can move to the next speaker. Next speaker, Elena Gandyul, please.
Am I still presenting or not?
No.
No? Oh, then that's okay.
Can you hear me?
Yes.
I can.
Oh, hello, everyone. Thank you. The research topic is devoted to the mitigation of numerical dispersion. Numerical dispersion in seismic modeling is a specific type of numerical error. Such an error occurs when modeling seismic field or solving the wave equation in an elastic medium using a coarse grid. Thus, the task of our research is to approximate the transition operator from one set to another, a set of seismograms modeled on a coarse grid into a set of seismograms modeled on a fine one. Let's introduce the notation. X is a seismogram modeled on a coarse grid, and Y is a seismogram modeled on a fine grid. The absolute difference between X and Y is shown on the right picture. Let's talk about motivation. The methods listed here for mitigation numerical dispersion have their disadvantages. In the first paragraph, methods such as the height order finite difference schemes, Galerkin methods, and other do not necessarily lead to a reduction in computational complexity. As the order of approximation increases, the number of operations and the memory used also increases. And post-processing and pre-processing suppress only temporary dispersion in second point. The seismic data we use in this research was obtained by solving the elastic wave equation defined in a two-dimensional unbounded domain. So we get the statement of the problem expressed here in terms of the differential operator. Our goal is to get the entire data set, which includes all seismograms modeled on a coarse grid. This can be done relatively quickly. We obtain them using the approximation of the differential operator. We assume that the norm of difference between a seismogram generated by a neural network and a seismogram modeled on a fine grid is much smaller than the norm of difference between the seismogram modeled on a coarse grid and the seismogram modeled on a fine one. Here we just reinterpret in terms of x and y. After modeling seismic fields, we proceed to the neural network training step. In this study, we used a numerical dispersion mitigation network, a slightly modified UNet architecture. Our neural network contains an encoder and decoder with interconnecting skip connection. The encoder captures the context of the image by reducing the spatial resolution of the input image through a series of convolutional and pooling layers. The decoder then recovers the original spatial resolution by using a series of deconvolutional and upsampling layers. So I will probably skip the description of the neural network itself, since this is not the main thing in this work. During the training, the parameter theta are optimized by minimizing this loss function. Theta is a network parameters, which includes the weights matrix and bias. We simulate the seismic data set using the BP model shown in this picture. The right part of the model consists of a simple background and slowly changes. In contrast, the central and left part is more complex and have a solid body and sharp velocity. From such a model, we get 2,696 seismograms. The sources are located at a distance of 25 meters. Next, we cut a 512 by 512 piece from the seismogram, such that. Let's talk about three methods that create training set. The first and easiest way is to take equidistant sources, that is every 5th, 10th, and so on. We conduct a Hausdorff metric between the positions of the sources that are included in the training sample and all variants of the position of the sources. Next, we build a sample from the consideration that the models corresponding to the close position of the sources are similar. The similarity of the seismograms correlates with the similarity of the model where the wave field propagates. We may consider a set of model M with the number of models equal to the number of sources, and a set of models that correspond to the position of the sources whose seismogram are included in the training data set. Then the Hausdorff distance between these two sets is D. Is this? D is a normalized mean square distance. The distance matrix is shown here. It shows how different the velocity models are. So if the matrix takes the values 0 or close to it, they either match or are similar. Let's draw a few lines of this matrix. Note that near the source itself, the distance of the source from the nearest varies almost linearly. To create a training data set, we just limit the previously introduced Hausdorff metric. And third, in the same way, we can construct a distance matrix for the seismograms themselves and introduce a Hausdorff metric. Also, we will limit it and get a data set based on the properties of the data itself. Let's present the results of neural network training on all three samples. The notation is here. The dependence of the average error between all generated seismograms and seismograms modeled on a fine grid is shown here, depending on the size of the training set. trends show that the best results when learning on the first two datasets. Next, we will already consider the learning outcomes or error depending on the index of sources. Here, it can be seen that with a smaller training sample size, dataset based on a distance between seismograms has approximately the same values as the rest. With the growth of the training dataset size, approximately the same training result on 3 datasets. Here we built random datasets and trained our neural network on them. The dependence of the average error on the size of the training datasets was constructed. We see that the error strongly depends on it. The dependence is nearly exponential. So we decided to fix the dataset size and conduct a global sensitive analysis for such a model. The model tells us that with a constant size of the training dataset, the error depends linearly on the metrics. Global sensitive analysis tells us how the parameters are most influential. The Sobel index is calculated for this case as a variation from the mathematical expectation of an error with a certain constant parameter divided by the error variation. For our model, it turned out that each of the deltas or each of the metrics affects the error equally. This graphic shows that potentially training on a dataset based on a newly introduced metric shows better results than training on a metric based on the distance between seismograms, for example. We saw that neural networks can be applied to seismic data and translated into more accurate ones. The neural network suppressed the numerical variance in seismic data by 3 or 4 times, which is essential for this type of data. Further, there were 3 different ways of forming a training sample, and we conducted a global sensitive analysis, as a result of which it was found out that the 3 introduced metrics are equally significant. Thank you for your attention. You can ask some question.
Okay, thank you very much, Elena, for interesting talk. Any questions, comments, please?
In the room, no.
Okay. I have a small question. You show application of your method to the two-dimensional problem. How do you think? Is it difficult to generalize it to the three-dimensional case?
I think it's not complicated to continue the research to three-dimensional, I think.
Okay. Let's hope. Okay.
Yes.
More questions? No. So Elena also saved a lot of time. So let's go to the next speaker, Kirill Gadirshin, please.
Hello, can you hear me?
Yes.
Can you see the presentation?
Yes, we see.
Good. Hello, everyone. My talk is the second talk in a row about the numerical dispersion minimization. And the title of my talk is the Frequency Domain Numerical Dispersion Minimization Network. So the outline of my presentation is as follows. I start from the introduction, then I briefly describe the numerical dispersion mitigation network in the spectral domain. And then I presented two sets of experiments. The first one is experiments in 2D, and the last one is a preliminary experience in 3D. So seismic modeling has various engineering applications, including exploration seismology, seismic monitoring of greenhouse gas sequestration, and earthquake engineering. However, it's a very computationally demanding procedure if conventional grid-based methods are used due to the mathematical restrictions on the grid size, especially if we are speaking about 3D modeling. It is well known that if a numerical scheme approximates the differential operator and is stable, the numerical solution converges to the true solution when the grid step tends to 0. However, reducing the grid step leads to a dramatic increase in the problem size and computational time. For example, in 2D, if we reduce the grid step by a factor of 2, then the computational times required for modeling of one common shot increase by the factor of 8. If we speak about FGD, then if we reduce the grid step by the factor of 2, then the increase in computational resources in computational time will be a factor of 16. So the idea of this work is to reduce the computational time to solve for this forward problem on a coarse grid, and then to apply the NDM-net to post-process the seismograph calculated on a coarse grid to make it similar to the seismograph calculated on a fine grid. So here we present the horizontal component of the solution for a fine grid at 2.5 meters and for a coarse grid 10 meters in the difference. And all the plots are all the data are plotted on the same scale. If we see on a single trace, for example, here the plot A is a full trace, a particular trace. A black plot is a fine grid solution, and red plot is a coarse grid solution. And one may see that the numerical dispersion grows in time. So here is a window from 0 to 1 second, and next two time windows is from 2 to 3 seconds and from 5 to 6 seconds. And one may see the huge errors in phase and amplitudes of the data, of the calculated data, as the time goes forward. So that means that numerical dispersion grows in time. But the current NDM-net applications doesn't allow to process the full seismogram at once. You have to split your seismograms, and as a result, we face the lower post-processing results. So the idea of this work is to try to compress your seismogram somehow, in particular by applying the fast Fourier transform in time, to make it possible to process the whole seismogram by calling the neural network just once. So on this slide, we demonstrate the pre-processing steps. So we have the original seismograms. The time length is about 6 seconds. Then we perform the Fourier transform. And we took not the full spectrum, and we use the reduced window. For example, if in this case we have a source signature is a recurve wavelet with dominant frequency of 30 Hz, and as a result, we see that the spectrum tends to 0. So about if you took the 512 time frequencies, then after that the spectrum is almost 0. So the idea is in this way we are able to compress our seismogram to reduce the number of samples by about a factor 4. And here we have the FFT real and imaginary part which are cut off from the full spectrum. Next, we performed the inverse transform. So we took the only significant values from this frequency range. Then we add the additional 0 values to have a initial number of samples. Then we perform inverse Fourier transforms, and we see that we almost we cannot see the loss in data by performing this transform. So the idea of this, and then we just pre-process all the data from time domain to frequency domain using the classical NDM-net with the slightly modified input tensor. So the NDM-net, let me briefly describe what is an NDM-net. It's a fundamental framework of our analytical study, and this is an adapted variant of the UNet, fully convolutional neural network. The architecture of NDM-net consists of 16 convolutional layers, 8 upscaling layers, 8 concatenation layers, and it is visually represented in this slide. The input and output tensors in this case are 512 times 512 times 2. So we have and two channels of the input tensors represent the real and imaginary parts of the seismograms in time frequency domain. Okay, to train the neural network, we utilize the pre-calculated seismograms from a fine grid corresponding to a common sort position, and their corresponding distorted versions generated on the coarse grid, and the seismograms recorded at the input and output of the NDM-net are acquired from the free surface. So once again, we create the seismogram in time domain, we perform the FFT transform, we cut off the singular spectrum, and we prepare the tensors of dimension 512 times 512 and 12 and times 2. And in this work, we just use equidistantly spaces training dataset using each 10th source positions. And then we split the entire dataset in the training and the validation set with the 80 and 20% ratio. Okay, let me start from the numerical experiment. To illustrate the applicability of the FFT-based NDM-net, we consider the BP velocity model, which is widely used as a benchmark for seismic processing, seismic imaging, and full waveform inversion. The P velocity is presented on this slide. The model combines the complex geological cross-sections from 3 different regions. This model size is about 70 kilometers in the horizontal direction and almost 20 kilometers in the vertical direction. And the acquisition system includes almost 2,700 sources with distance between each equal to 25 meters. The active recording system of each shot includes 512 receivers with a maximal offset of 7 kilometers. With a Ricker wavelet with central frequency, with a peak frequency of 30 Hz, and to simulate the wave fields, the synthetic seismograms we use for further accurate in space and second order in time staggered grid finite difference scheme. To restrict the computational domain, we applied the perfectly matched layers. So in this notation, the fine grid solution is a solution with a grid step of 3 meters, and the rough grid solution is a solution with a grid step of 6 meters. And to quantitatively assess the level of numerical dispersion, we just use the following relative error estimation. We took the L2 norm of difference between two seismograms, scaling by norm of reference seismograms, the seismogram calculated on a fine grid, and multiplied by 100%. And following this formula, for this particular testing seismogram, the level of numerical dispersion is about 103%. So which level is unapplicable. Next slide is a training curve. So once again, we perform we can generate the training data set using 10% of equidistantly spaced sources from the full acquisition system And here's the training curves. The training validation losses and the best value are indicated by the error. So we took the NDM-net weights after the 74th epoch. On these slides, we demonstrate the prediction examples from the testing data set, which is not shown by the NDM-net during the trainings. Left and right, two testing samples, and each column is a real and imaginary part, and from top to bottom, the 6 meters, the coarse grid solution, the NDM-net post-process data, the fine grid solution, the original level of numerical dispersion, and the reduced error after the NDM-net post-processing. And one may observe that we were able to reduce on this particular in these particular examples, we were able to reduce the level of numerical dispersion by the factor of 3. Here we represent the numerical dispersion curves. This is the same relative error, but plotted with independence of source index. So with the original errors is close to 100%, and after the NDM-net post-processing, we were able to reduce up to the factor 3. We were able to reduce the level of numerical dispersion up to the factor of 3. And if we come back from spectral domain to the time domain, and we obtain, following the Parseval's theorem, the L2 norm of FFT seismograms are the same as L2 norm of original time domain seismograms, and we see that, and so this seismograms is calculated just by applying the inverse Fourier transforms on these test samples in frequency domain. So first, the A is the coarse grid solution, the B is the NDM-net post-processed seismogram as applied to the coarse grid solution, and C is the reference solution, so-called fine solution. As a 3-meter solution, D is the regional error. Regional relative error is about almost 100%, and the right column is the error after the numerical dispersion mitigation process. On this slide, I present the same, but for a single trace. So this is F is here the red plot is a coarse grid solution, blue plot is NDM-net post-process trace, and black plot is a fine grid solution. And we see that blue and NDM-net post-process seismogram is very close to the fine grid solution for both time and frequency domain. And in the end of my presentation, I wish to briefly demonstrate our preliminary works for 3D. So what we did, we took the benchmark 3D SSG overtrust model. The red line indicates the short positions line. The model is about 20 times 20 kilometers in lateral dimensions, and about 5 kilometers in depth. So in this 2D line, in this line, we have 200 shots. We use for simulating the data, we use the source signature was a record with a peak frequency about 15 Hz. The time sampling was 4 milliseconds, and the number of time samples is 1,250. The maximal offset for each common shot, the maximum offset in X and Y direction is 5 kilometers. As before, we took the 10% of equidistantly spaced sources, and the training data set is 20 shots. So in this context, the fine grid solution is solution with the grid step 12.5 meters, and the rough grid solution, coarse grid solution, is solution with the grid step of 25 meters. I skip the description of 3D numerical dispersion mitigation network, just some preliminary results. This is a prediction example from a testing data set. That's one slices. In a slice, the slice coordinate is y offset is minus 4 kilometers. First plot is 25 meters. Second plot is corrected, is 25 meters after application of TMDMNet. The third column, the third plot is a fine grid solution. In the original error of numerical dispersions is about 53%, and after the mitigation is about, after application, the 3D NDMNet is about 11%. This slide is for offset. The offset is close to 1 to the source position. 50 meters, the same. We face this similar numerical dispersion mitigation factor of about 5, and the last results for y offset for 3,500 meters. And this is the numerical dispersion mitigation curves as a function of source index. So one may see that for 3D, in this particular example, for 15 Hz recurve wavelet, we obtained for 3D seismograms, we were able to reduce the level of numerical dispersions up to the level of 5. Okay, thank you for your attention. Any questions?
Thank you, Kirill, for your talk. Any questions?
No? In the room, no.
In the room, no questions.
No.
Yeah. I'm also have no questions. I see only that it is very challenging topic, very interesting, and you should continue this research. Okay, thank you again.
Thank you.
Okay, so the last speaker is Sergey Solovyov. Please.
Okay. One moment. Can you hear me?
Yes. Yes.
Okay. No. No, it's... one moment. Okay. Can you see my presentation?
Yes, we see.
This research is performed in scope of project of modeling bioequation in quasi-static state and in frequency domain. This slide is about problem statement. On microscale level, we can see the porous space with various geometry, which is the reason of an anisotropy. And also various porous spaces are reason of two wave-induced fluid flow types on mesoscale level. These types are fracture to background and fracture to fracture type. All these factors should be taken into account while developing effective numerical algorithm to estimate wave attenuation. In our project, we work on mesoscale level and perform an upscaling. This slide is about upscaling and how to do it. The goal of upscaling is construction the homogeneous viscoelastic media, which equivalent the porelastic fluid saturated media. And to do it, we want to develop the numerical effective algorithm, which should be accurate, fast, and memory saving. There are two steps of this algorithm. The first step we should to create numerical solver for of bioequation. The second one is the reconstruction, the effective stiffness tensor, and the last point is the estimation, attenuation, and phase velocity. In the current presentation, I will talk about the first point and how to satisfy these three criteria: accurate, fast, and memory saving. And we solve the bioequation with three types of laws: the horizontal pressure, the vertical pressure, and the torsion one. With this boundary condition, we should to solve this equation. And we consider the rectangular computational domain with the rectangular mesh and equal vertical and horizontal steps of this mesh. The boundary of this domain cross the mesh at the center of edges. After that, we use the finite different approximation with media properties located in the center of cells, and unknowns of equation are located in the center of edges. And also the equation are approximated in the center of edges. And the result of such finite different approximation is the system of linear algebraic equations which well-known properties. The first property is that this system with complex arithmetic, the matrix A is non-symmetric and non-Hermitian matrix, and these matrices are singular, so it's not good properties of Slyer to solve it. And we know that there are two approaches to solve a system of linear algebraic equation: the direct solvers and iterative solvers. And here you can see the result of modeling by direct solver. By direct solver on the mesh with 500 points by 500 points, mesh points with 30 frequencies and 6 fractured models with various connectivity with cracks. And the right side, you can see the N chart of attenuation and performance, and you can see performance result. It's some summary of performance result. We spent just half hour to perform computation and for this model characteristic. And the details of these experiments we presented before, and now we want to do the next step, to do the 3D modeling. But my experience shows that the direct solver are very heavy in terms of memory usage in compare with the iterative solver. So we need to develop the iterative solver and test it on the current 2D model. And now we will talk about iterative approach. Based on system equation properties, we use the biconjugate gradient stabilized method, iterative method, BCG stub. We try to use several preconditionals, for example, Jacobi, block Jacobi, but the best result it's using the field split technique to precondition for preconditional for create preconditional. This slide just about the BCG stub algorithm, and I will not comment this. Just some remark about stop criteria. At each step of BCG stub algorithm, we compute the effective stiffness tensor at each step and control the value changing, how fast it's changing. It is doing because of the traditional relative residual criteria is not informative for such a problem. And another feature, we use the field split precondition. Now I will talk about this technique, field split. The finely different approximation of bioequation can be considered as approximation of two pair equations, first, second, and the third and fourth. And in each pair of equation, we consider the velocity approximation and the fluid velocity approximation as well. And such separation leads to blocked slide representation. If we remove this blue block, fluid flow approximation part from the first pair of equation, we get the blocked low triangle system of equation, which can be solved but pretty simple algorithm. At first, we should to solve this slide like elastic equation approximation. After that, recompute the right-hand side, and after that, solve the fluid equation. In fact, that inversion of the full matrix A in direct approach, we substitute by inversion of two smaller matrices on each step. The A0 and A3. And they also can be reversed by either direct solver or iterative solver. At first step, we use the direct one to inverse A0 and A3. Why we do it? Because it needs to investigate the properties of our iterative process. So we need to create the robust inversion of matrix A0 and A3. It's very important to the robust inversion to investigate iterative process. And the first matrix A0, it's the like elastic matrix. It is a symmetrical, positive definite, and with the real coefficients. And let me know that matrix A0 it does not depend on frequencies and can be factorized just one time for all frequencies. But the second matrix A3, it's complex arithmetic, and it's not positive definite. And here coefficients depends on frequencies. But on the other hand, the number of non-zero elements of A3 is less than in A0 because the mesh tensor for approximation this part less than simpler than for this part. And the next slides are about the numerical experiments for estimation complexity of inversion these matrices. About the behavior of full iterative process and compare it with the direct solver of full problem. In these experiments, we compare the computational characteristic of two solvers, of direct solver and iterative. And we want to check the convergence of the proposed iterative solver, the number of float point operations, and memory usage calculation. And the measured results are that the first result, that number of iterations with field split preconditioner is a fixed. It's just 4. And it does not depend on problem size. The second one result is the number of flops of factorization is increasing as from 8 to 11 times, while we increasing the mesh size. And increasing the memory coefficient, it's about 4 and 5. And of course, the direct solver could not solve very big problem, the biggest problem, and iterative solver can do it. And what's the conclusion of this research? We proposed this iterative solver, and the main result that this solver converge while we use this field split preconditioner. Converge doesn't depend on task size and frequency value, and we can solve problems which bigger than direct solver, so we can move from 2D equation to 3D equation. And convergence rate can approach 10 times and compare with the direct one on these models. So we can be faster 10 times. Some remarks that in reality the computational times not 10 times less than direct one, because the direct solver is highly optimized, and we should to continue optimize our iterative one. Okay, thank you for your attention and your questions.
Thank you for your presentation. Any questions or comments, please?
Yes, one question in the room.
Yeah, please.
Yes.
Okay. Yeah.
Hi, Sergey, thank you for your presentation. I'm Irlan. Can you hear me? Nazarbayev University.
Yes, I hear you.
Okay. Thank you for your presentation. It's a great talk. I was wondering about when you say the direct solver, does it mean it's LU method or certain kind of solver that you are using? And the second question is it in parallel or are you using the single processor, single core?
Okay, I understand.
Because you compared with the direct solver, right? Mm-hmm.
Yeah. Mm-hmm. We does not develop own solver. We use the highly optimized direct solver for sparse system of linear equation, which developed by Intel MK library, the Pardizo solver. Do you know such one? Pardizo.
Huh?
Intel MKL. Intel.
Okay.
Intel MKL Pardizo. This direct solver.
Okay.
I can write.
Oh, okay.
I can write.
Okay.
And this. One moment.
Oh, MKL. Okay.
Yes.
The partizo. Okay.
This
So it
highly
must be.
optimized parallel, OMP parallel. Yes.
It should be parallel, right? I see.
Yes, yes, okay,
It
of course.
means, thank you. And the second question, what was the structure of the matrix overall in this field phase biot system that you are inverting? Was a particular structure it has or not?
Yes, it's not. Moment. If you talk about this full matrix, can you see my mouse?
Yes. Okay. So it's block form. I see.
Yes. This all matrix A not have very very not easy structure, and when we approximate it, we save it in the compressed parse row format, not diagonal, compressed parse row format. In terms of diagonal, I think that the matrix A have about maybe about 30 diagonals, 30 diagonals, non-zero diagonals. Or maybe you mean some another in your questions.
No, I was interested on the structure of matrix. There are many methods, right? And for the Krylov, it's kind of belongs to the Krylov subspace method, and even there exists some parallelized version of that. I was the next question, if you may, how you compute these flops? Did you take it from your software?
Okay, this gigaflops is the result when we run Intel MKL Pardizo. They provide the number of flops, and we summarize them and provide this one number of flops. It's some result of solver.
Okay.
Black box.
Okay.
Number of non-zero elements we estimate also by result of solver and by memory estimation on hardware.
Okay. Thank you very much. Great presentation. Okay. Thank you.
Thank you.
Okay, so we have no time anymore. We should finish our mini symposium. Thank you again, Sergey, for your talk. Just for your information, the second part of mini symposium will be in 20 minutes in room G. Thank you.
Thank you.
Thank you.
Thank you.
start. Don't worry. We'll finish fine.
Because tonight it's
Okay, I'm so sorry. Yeah, of course. The workshop, the session start in 10-50 minutes. I'm so sorry. Hi, this section is open. We can start.
Yes. Okay. Yes. Dear distinguished professors and colleagues and participants, I greet you all with respect. I'm Iris Karaca from University of Massachusetts, and first of all, I would like to express that I am delighted to have been invited to this conference. And on this occasion, I would like to extend my sincere thanks to Professor Osvaldo Gervasi and committees for such a fruitful and successful organization ongoing for several years with dedicated and devoted efforts. I would like to also thank everyone involved for their hospitality. And the chair of our workshop today will be me, Iris Karaca. I am pleased to meet you and to be here with all of you here. Today, first presentation. Okay. Just a moment. Yes. Mr. Julia Disogus is our technical assistant who will kindly be assisting us today. Thank you all. The first speech we are going to listen to is related to delivery of the paper entitled Analytic Solutions of Fractional Differential Equation associated with the key symbol Tremblay and differential operator by Rabba Ibrahim, Susan Obeis, Nur Amelina Minti, and Yes Karaca. Floor is yours, please. I think that
Yes. There is.
okay. Next presentation. Okay.
Yeah. The first is in presence, but there isn't. It's okay.
Okay. Okay. Okay. Next presentation. Well, dear participant, at this point, let us proceed our workshop with another paper whose title is Fractional Order Computing and Modeling with Portraying Complex Fit Real-World Data with co-authors Iris Karaca, Matteo Rahman, and Dimitru Baliano. Let me... you may start your presentation, please, Dr. Matteo Rahman. Are you with us? No? Yesterday, yes, he informed something me. Let me kindly note that Dr. Matteo Rahman is not going to be able to attend due to his health situation, as he stated. So we can go to next presentation. I think our next presentation is on the paper entitled Forecasting Multivariate Time Series with a Dynamic System-Based Hybrid Model by Jonave and Anna Golovkina. Please. Okay. Daria, yes. Yes. You may kindly start, please, if everything is settled and ready.
Please, where is?
Okay.
It's on this. Okay, one moment.
Let me take your hand.
Why not?
Presentation, can we go?
No, because.
Views?
Oh, perfect. Okay.
Okay, hello, dear colleagues. I would like to present a part of my research dedicated to forecasting of multivariate time series with a dynamic system-based approach. At first, I would like to start with the motivation. Why should we use a dynamical system to predict time series, and for what reasons that could be useful? I think you know that dynamical system is a quite common type of representation, time evolving processes in nature, in physics, in science, and somewhere else. Usually we used to make a modeling in order to describe the observations that we see surrounding us. The typical mathematical expression for dynamical systems is ordinary differential equations or some kind of iterative maps that are built upon the laws of the nature. But if we try to build that model for some particular process or some particular observations that we might have, it could be not so easy to do so. And usually people say that modeling is an art, and as art is an expensive thing. That's why appeared a lot of other approaches, like black box approaches that uses some machine learning techniques, probabilistical, statistical approaches and analysis in order to build some kind of model for the observations that we might have, for the time series that we have. There are some limitations, of course, with these approaches. Usually, it's hard to use such models to get the predictions for the unseen inputs, for example, to use them for generalization and for extrapolation purposes. That's why it's so attractive to combine our old school methods like dynamical system reconstruction with the modern techniques that we now have. Of course, why that should be needed for us, because if we have a dynamical system model built, we can use a variety of well-developed theories to solve various problems like short-term prediction, autonomous control, fault detection, and even root cause analysis for the observed fault in the time series that we have. A couple of words about the existing approach to dynamic system reconstruction. The most, I think, famous library nowadays is PyCindy libraries that considers a system with a state that governed by some unknown ordinary differential equations. And the purpose here is to recover this unknown function f from the measurements that we have. This unknown function usually is found like a linear combinations of some candidate functions. So we have a library like trigonometrical polynomials, simple polynomials or other functions, and the only thing we need to do is to find the coefficients of these linear combinations based on the time series that we have. But it works on quite not narrow, but not general case, because in real systems, usually we can have missed values in our observations, Other measurements could be done through the large time intervals. All these factors limit the capability of this approach to recover the dynamics of the system behind the time series that we have. And for example, if we compare the reconstruction results when we have regularly or irregularly distributed time series of our measurements for a simple model, we see that this approach by Cindy hardly can reconstruct the true dynamics of the system. We propose to fight with these factors by making some pre-processing, pre-processing of the data that we have. Here I will show you the results of this approach on the real data example. And here, at first, I think we should focus on this solution pipeline. So at first, we should make a pre-processing of our time series data in order to fill that gaps. And we propose to use some approximations of the data using some splines and so on, and use this approximation in order to generate artificial points to fill these gaps. After that, we have time series equally distributed in time, and it could be easier for further processing. After that, what we can do? Usually in the real time series data, of course, so we have some noises, some other factors that could influence on the dynamics of this time series that are not observed, or we can explicitly take them into account. So in order to make the dynamical system reconstruction, at first we propose to decompose the original signal into deterministic part that will be used further for the reconstruction, and statistical part that we will try to describe by some statistical approaches, simple machine learning models. And then we combined the predictions that we made using the dynamical system and that we use using the statistical model all together. And interestingly, that this approach gives us quite good results compared to simple traditional prediction models. And I want to illustrate this technique on the real-world data set. It's a Abelina network. It represents 12 connecting nodes, and each network edge that we see is the transmission of the traffic between the nodes. We have the measurements of traffic in 5 minutes time, and the problem here to be able to predict traffic between particular nodes in this system. Why this should be useful for us? Because if we can predict traffic, then we can control, for example, the load of these transmission nodes. We can switch on or switch off some stations if we know that there is going to be traffic increase or decrease, for example. So at first, we make decomposition of the time series, and it looks like that. So we have the original time series, and we try to extract from it its dynamical component, that it's smooth enough in order to be used in dynamical system reconstruction. And statistical component, what is left, is shown below. After that, you remember that in our system we have 12 nodes, and if we want to build such a large system, it's quite computationally complicated. So at first we made a clustering of all of our data to join them into the groups of most influencing nodes. And then we reconstruct a dynamical system for each of the group independently. So you can see here the results. We decomposed the original time series into dynamical and statistical components. And here you can compare that original time series and the predicted time series. And then we sum up to make the composite forecast that you can see on the right part of this slide. And we compared the proposed approach with simple machine learning models for univariate time series forecasting. It's SVR and the RIMO model. You can see already visually that this approach looks better. And if we compare the metrics of our approach and those approaches also for a different prediction time horizon, there are also a quite huge difference between them. And also, what is more important, this approach is quite robust to the horizontal forecasting. You can see that the mean absolute error is almost the same if we forecast for 1 hour, for 2 hours, or even for 24 hours ahead. So the conclusion slides, I don't think it's necessary to repeat all the things. Yes. So if you have any questions, my presentations, I would be glad to answer them. Maybe some questions online.
Thank you for your presentation and your research, in which there is a time series forecasting approach. You integrated non-linear dynamic systems. You are working non-linear dynamic systems. Yes. Very nice presentation. Thank you very much. Yes. Okay. Now we are going to listen the presentation of the paper named "Decision Support for Effective Urban Regeneration Projects: A Model Based on Community Interest, Project Post Analysis," with the co-author who are Ivan Bilecic, Emmanuel Moroni, and Valeria Seu.
Sayu, there isn't.
There isn't.
Yeah.
Okay. Okay. Next, we may proceed with the next presentation in our workshop. The paper is sensitivity analysis of a cardiac electrophysiology model for the occurrence of electrical alternance with the authors Rodrigo Pigozzo, Rodrigo Weber dos Santos, and Bernardo Rocco. If you are ready, you may kindly start, please. Thank you.
Hello.
Hello.
Do you listen?
Yes.
Okay. So, thank you so much for the opportunity to present my article in this ICCSA Congress. My name is Rodrigo Bittencourt, and my work that we'll present now has as its subject sensitive analysis of a cardiac electrophysiology model for the occurrence of electrical alternance. So let's move on to the job overview. First, I will briefly introduce the subjects to be addressed in these slides, which are the result of the article, and they also tend to respect the same order. The second point, I will show the motivation behind the, we redress this issue of in our article that was written for this conference. Third point, I will show the modified Mitchell-Schaeffer model, which is a cardiac model that helped us to study the occurrence of the electrical alternance phenomenon and its methods to find it. Fourth point is where I will talk about the methodology used about the model parameters and its approach limits or bounds, about the number of samples implemented, about OpenCarp, which is an open simulator of cardiac electrophysiology for in silico experiments, and about the analysis made of APD, action potential duration, and max slope, maximum of restitution curve for each parameter, and one at a time, to show their impacts on these quantities of interest that we defined, and consequently to show their impacts on the occurrence of alternates. Fifth point, I will talk about the conclusions we issued with this article. Sixth and penultimate point, I will talk about our work in progress. Together with my advisors, I will now address another sensitive analysis known as MCF, Monte Carlo filtering, and its respective initial impacts on the modified Mitchell-Chef model. So, and the last point, our reference. This introduction is cardiac. So, introducing ourselves in the context of the article, let's go to the first point. What are cardiac arrhythmias? They have an impact on our heart rate and the health problems. We can lead to cardiac arrest and death in humans. We saw a study that the electrical alternates are frequently seen in patients with cardiac arrhythmias, particularly those that affect the ventricles. Therefore, the importance of identifying and monitoring the phenomenon of electrical alternation arises to prevent serious complications in patients with cardiac arrhythmias.